Okay, so I switched over to the supply that I make for the Apple TV X and the Switch X and all that, and you can see that I use remote sensing. That's these little two wires, so that's important to get down to the really low noise levels. These noise levels are so low that they're difficult to measure. Anyway, so this is the same current and the whole same setup that we saw a second ago with the really gnarly high-end linear supply. The same amount of current, same pulse width, but you'll note that the total amount of noise here is magnitudes less. So, so the total peak to peak is 1 millivolt. The total RMS is 172 microvolts of noise. And you can also see this is really clean. The current waveform is perfect. It's square. It is really doing what it's supposed to do. The noise, the voltage regulation is doing just exactly what it's supposed to do. But it's, nothing's perfect. But remember the differences in level here. So what you're looking at is 10 times less than the other supply. So, and we can look at all of this. So what happens is the load comes on, it's very sharp. So that means the power supply is delivering this current just instantaneously to demand. So it's not fooling around. It immediately delivers that current. The regulator goes whoa and brings it back up, and then has kind of a second look at it, and then we get this line, and then it comes back and it lets go. And but these are quite clean. Let me switch my trigger over the other way, and we'll take a look at this front, the turn on. Okay, so if we look at the turn on, you can see that this is quite clean, and really there's not much of an issue there. That goes straight down, comes right back, and then just goes into it. So there's none of this weird stuff like what we saw in the last one. There's no leftover recovery. You can see that. So it's very square, which is important too. So okay, so how's this work at different frequencies? Well, let's go find out. So this is a low frequency. We're going to go to a 1 kilohertz equivalent. So let's go look at that. All right, again, we've got basically the same waveform. We've got a little bit more noise, but we're still, a very, very low level of noise. The waveform's extremely square and clean. Still good. So let's go ahead and let's go up to a 2 kilohertz equivalent. Look at that. Now again, it's basically the same level of noise. Getting a little bit more, 360 microvolts. But again, the waveform's quite square. Everything is extremely sharp, and there's not a lot of other noise on the waveform. These are very thin lines. That means that there's not a lot of background noise either. So let's go ahead and go up to 5 kilohertz equivalent. All right. So now let's take a look at that. Again, basically exactly the same thing. The frequency response is just dead even. We don't have any real changes that are going on. This is again 360 microvolts RMS. It's still about 1 millivolt peak to peak. It's a very, very low amount. And we're at 5 kilohertz equivalent. So let's go ahead and go to 10. Okay, so now we're going to go up to 10 kilohertz equivalent. And again, this is all really quite square compared to some of the other products where they start to get really messy. We're still at the same amount of noise. We're still at the same amount of amplitude. So the power supply is delivering the same amount of current at all of these frequencies evenly, and we're not changing anything in noise. So that means it's very flat, controlled frequency response. So now let's go up to like 50 kilohertz, where it's going to start to get a little weird. So, okay, so now we're going to go up to 50 kilohertz. This is way beyond where I was testing the other device. Again, this is actually quite clean considering the frequency. Got a little bit of ringing going on, but the noise, again, we're still at the same noise levels, and it's still delivering current even at these high frequencies. So that's for really tiny pulses. That's really important if you're going to be delivering packets and you're going to be delivering HDMI and you're going to cover all these really small little changes in current. Your supply has to be able to do that. Okay, so let's go up to 75 kilohertz. What the heck? So this is 75 kilohertz, and again we're still getting basically a pulse, a pretty square pulse, and we've dropped a little bit, so it's not quite supplying as much juice, but it's close. Also, our noise level is really just where we were. So even at this high 75 kilohertz level, we're still hanging in there just fine. These high frequencies, the power supply doesn't really see, because the filter network and the capacitors and the things on the boards themselves handle all these high frequencies before they get this far. But I made sure that the linear is extremely wideband anyway. So let's go higher. Let's go to 100 kilohertz. This is getting substantially above anything that the power supply would really have to do. I think I did that right. Yeah, didn't I? Yeah. So that's 100 kilohertz, which is, this is, let me get this out of the way so I can see it. So this is a 5 microsecond pulse. This is really kind of ideal. There's not a whole lot of extra ringing and noise here. I mean, it's doing a reasonably good job considering this 5 microsecond pulse. And keep in mind, this is at half an amp, which is more than the power supply ever delivers to this gear. Like the Apple TV deals with 120, 180 milliamps, so it's substantially less than this. And the performance at the lesser levels is better than what we're doing. The performance at these higher currents is more difficult. So let's just go crazy. Let's go to 150 kilohertz. Okay, so now what we're going to do is 150 kilohertz. We are going to run out of its ability to do this, but even at 3 microseconds of pulse, we're still at 575 milliamps. So the power supply is still delivering a really pretty clean amount, and with a really small amount of noise. That's 400 microvolts of noise. So to put this in perspective, let's look at the whole frequency response. So now what I'm going to do is I'm going to drop it down to a 100 hertz, so way down low, and we're going to see what those numbers are way down here. So way down here, we're at 585 milliamps for the amount of current, and our noise is at about 1 millivolt and 130 microvolts. So if we go back up to 150 kilohertz, hold on, I gotta get that little tiny pulse all zoomed in. So now we're going to go to the extreme range. And we're going to look at the difference. So we were doing 586 milliamps. We're at 577. So it's still delivering current quite accurately. And our noise, 1.2 millivolts. So, and 400 RMS microvolts. So this is It's very similar across the entire spectrum band. And that's what's important, is to have a really flat, wide response no matter what you're doing with it. That's really important. So that's how a good power supply should end up. Everything else I test pretty much doesn't get anywhere near these kinds of performance numbers. It's all just pretty much, I don't want to say garbage, but let's just say it's not well engineered. I hate to say that, but these tests and these measurements need to be done during linear power supply development so that it works fully, correctly, with high performance, especially at the numbers that these cost.